Yeah.
To your presentation today.
Oh, awesome. Great.
Yeah.
Um, yeah, okay, great. We're recording. All right, cool. Yeah, so I figured I would just start off with some basic examples, just kind of show you guys, just some instances of how this rolling implementation is working in K-Framework currently. And then we can dive deeper into the code if you guys are interested in that, or just want to see examples. That's totally cool.
One thing that would be helpful is to get a better understanding of the relationship of K-frame to R-chain to rholang and how it fits in.
Yeah, so the reason that we're using K framework and trying to do an implementation of rholang in K framework is so that we can do formal verification of basically every part of the code that we write. So K framework is a great tool. Basically, what it allows you to do is define a language, and then from the definition that you create, it's an operational semantics definition. You can immediately take a bunch of formal verification tools. It generates parsers, interpreters, all sorts of different tools for you to use once you define your language in K-Framework.
So this added structure is going to provide us additional security, so you won't have issues like the DAO bug and those things like that. It's this rigid structure won't allow for one-offs to happen. Is that sounding
That's right. Yeah, exactly. We
okay?
can we can show all of the possible behaviors of a particular program before we ever even execute it on a blockchain.
So
And,
this
uh,
is important. This is
you're
important.
creating an interpreter so you can actually run programs in that language that you define, right?
Yeah, that's right. Uh-huh.
And this is becomes important as the R chain starts to scale and get bigger and bigger. If you're doing 40,000 transactions per second, any type of issues that you have gets magnified at that
Yeah,
level. So everything's got to be rock solid
that's right.
when
Yep,
you're running at those speeds. And
exactly.
and this is going to help us get that structure that we want.
That's right. Yeah, you hit the nail on
Cool.
the head. Yep.
Cool.
Yeah, so I'll go ahead and share my screen so you guys can see what's
It's
going
more
on.
about evolving rholang, right? In terms of
Well, yeah,
improving rholang.
right. Improving the rholang, not necessarily the R chain infrastructure, but the rholang language that we're going to be using to write the smart contract. So, thanks for that
Yeah.
clarification.
Yeah, absolutely. Yeah, so this is technically a different language that is trying to resemble Rholang in every way, shape, or form, and so that we can get those formal verification tools that I was talking about earlier.
Okay.
Yeah. So let's just start with the absolute most simple program possible. And if you're really paying attention, you'll notice this isn't actually a closed program. There's a free variable at the top level, but that's okay because when we execute this, it'll actually tell me that there's a free variable at the top level. I'm still saying that's okay for right now, but there's a really very easy thing that I can put in place that will just not even run something like this. But either way, so I want to run this com string. So first of all, something really nice about K framework is all of the rules that I'm defining for how a program should execute. You can give all of these rules names. So the name that I've been using for basically all of them is the com rule, because everything comes down to the com rule. So you can actually tell K framework to reduce things according to this com rule, and this will give you some non-determinism. It'll capture if there are two possible reductions. It will record both of those reductions essentially, as long as I tell it that this com rule is one of my transitions. So that's what I'm doing here when I'm saying to compile this stuff. So this Java backend is kind of just like the default thing to compile in. And then this transition com is actually saying that this com rule is one of my transitions, which allows for this non-determinism. And we won't see it in this example because there is no non-determinism here, but we will see it in some later examples. So it takes maybe 10 seconds to actually compile it, but I just wanted to do it in case, I don't know, anything weird happened. Oh, of course, what the heck is going on here? Well, that's very strange. Okay, working 2 seconds ago, but that's okay. It doesn't really matter so much. So we want to compile this one, or run this one. I feel like it's one of those things where anytime we're recording something, it automatically just throws like 10,000 parser errors, but we'll figure it out.
Yeah,
so
I pause the recording while we learn a little bit how to fix things from you.
Yeah, right. So, all right. So let's just talk about how this thing should execute, right? So we're sending this string hello on this channel X, which is just a variable. It's not, a well-defined channel name yet, but that's okay. And we're doing this in parallel with a listen on that same channel X. We're just listening for something we'll call Y. And then when we receive that Y, we're just going to concatenate it with this world, right? So hopefully what should happen is we get a COM event on this channel X, and we see hello concatenated with world, and it comes out with hello world. So let's see what it gives us. So here's the entire result. It starts with this result equal K, and then it shows all of this stuff here. And so this stuff starting with this T cell, and it has this thread cell. Oh, I know what happened. I did something really stupid. It's okay. I'll mention it later. So we have this red thread cell, which contains this green thread cell, which contains this white K cell. This is basically holding all of the different processes that are running in parallel. So in the end, right after everything is executed, I should only end up with this hello world. And so this is what's sitting here. And since it's a string, strings are ground terms. They don't execute anything. They just kind of sit there waiting. So this ended up in the K cell. So just to take a step back, actually. So what I asked K Framework to show me was when I run this code, right? So krun is the command for that. So when I run this code, which was what I showed you there, I only want to see the final states that come out of this thing. So that's what this search final is. And the search is in lines with the transition that I declared at the beginning. So I declared COM to be a transition. And so it's going to search for all of the final states with respect to this particular transition.
Now in tuple space, we have the sends and we have the receives.
That's right. Yeah.
How does this relate to the tuple space?
Yeah. So I'm just calling it this, right? You can call anything whatever you want. But when I first started building this, in my mind, the tuple space was the thing that held all of the different sends and receives, right? So I just called this particular cell the tuple space cell. But just like this threads or thread cell, it's just another cell. This is the configuration of the program that we're looking at here. And so just like you were saying, Jim, this tuple space cell has the send cell, which is going to hold all of the sends that are in this particular program. So at one point in time, this send cell held something corresponding to this particular send. But what happened in the evolution of this program is, well, we actually had a COM event, so it took that send out of the tuple space, and then we actually have just the continuation that's ending up, in a place to be executed further. But of course, it's not, because it's just a string. And then this receive here, there would have been a cell in that in this receives cell corresponding to that particular receive. But again, there was a COM, so that receive was pulled out. The send and the receive are both consumable, so they went away when we did the COM. And then this next location business is just about when I'm defining unforgeable names. It's just an index, basically, to assign to these unforgeable names. And then everything here is essentially not needed. But basically all this is doing is just so I don't have to flip back and forth between, my text editor and this terminal. I just have it print, the original program that I intended to run. So here's the original program. Maybe I can make this a little bit bigger. All right. So here's the original program that we ran, right? We just sent hello on X and then listened on X for something called Y. When we got it, we concatenated it with world. And like I said, there was a free variable on the top level. That free variable was X. And in fact, it was a name variable. So this is basically just telling me my set of free variables is one thing, it's X, and that X has type name. And then this debrunified stuff is just for alpha equivalents or structural equivalents. And basically all it's going to do is rename all of the bound variables just by indices, essentially. So you see instead of Y here, it's just got like a bound N of 0. Okay. Any questions about that, or is that more or less clear what's going on there? So this configuration captures everything that can happen in the program, essentially. Yeah, what's up, Thomas Hawks?
Oh, hi. Just a question about free variables.
Yeah,
this is just for you to see what's happened, right?
Yeah, that's right. That's right. Yeah. So like I was saying, this original free vars and debrunified, these cells are totally unnecessary for the execution of any program, but it's just nice to be able to see what's going on. Yeah, so this is kind of just like a nice log of data that is associated with the program. Yeah, so all right, cool. So we did the absolute most simple rholang program ever, right? Hello world. So all right, let's see. So let's make it a little more interesting. So here we're going to have same send and receive that we had before, but also in parallel, we're going to run another send on exactly the same channel. So we should have a race condition here because we're sending two things to this channel X, but we're only listening for one thing from the channel X. So we'll go ahead and run that. This one is just same thing, but with a 1. And again, I'll do the search final, so it'll capture this non-determinism and hopefully display the two results that it should have. All right, cool. So, okay, we see we have two results, or at least two results, because this has this OR here. So basically what it's telling me is, from my searching of all of the final states, here's one of the results. So one of the results was the goodbye message being consumed by the receive. So then we would get goodbye world. And you see that we have a send still in the tuple space in the sends cell. And you can see that this is the one that had channel X. Well, of course, both sends had channel X, but more particularly, this is the one with message hello, which is exactly what you would expect. The message goodbye was consumed, so here we're just left with hello. And then this stuff is basically just for matching purposes, and so this one is just telling me there was only one message that I sent. It was just a single string. This one's just telling me that it's a consumable send. So when it matches with a receive, it'll be taken out of the tuple space instead of persisting. And then again, those three cells that kind of just tell me, okay, here's the original program that I parsed. It still has that free name X. We expected that. And then kind of for alpha equivalence, I have the indexed bound variables there. And then, so that was the first result, was we got the goodbye message to be consumed by the receive. So of course the second result is, well, the hello message is consumed by the receive and the goodbye message is just going to be left there. And that's exactly what happens. So the hello is consumed. And so when the hello message is consumed, well, we concatenate it with world. So we end up with hello world, just like in the first example we saw. It gets stuck in the K cell because there's no further computation that we do on a string. Just as we expect in the send cell, there's this goodbye message still sitting there. So if we had another receive listening on channel X, we could also consume that message, but currently there's nothing else to have a COM event with. And same stuff here. It's literally exactly the same as in the first result. But basically what it's telling me is that there are two results and only two results from this particular program execution, right? Goodbye world and hello world, exactly as we would expect. All right.
Is it too early to ask? Can you somehow choose which reduction you want to see?
Yeah, so
For
that
example,
is
if you have
something.
multiple nesting.
Yeah, that's something that I intend to add to this, but I haven't gotten around to it yet. So I would definitely like to. I'm just not sure how to display the possible choices and then make all of that stuff work. So it's something I kind of put aside, but it's still in the back of my mind, kind of.
Cool.
Now, what would it take to actually run the program? And maybe, I mean, you are running the program, sort of. I guess I don't understand what having the free variables means, if that's a problem or not.
Yeah. Mm-hmm.
Just as it is, I think it's awesome, and I would really like to see it running on Robot. I think.
Oh yeah, okay. We can talk about how to set that up. That would be cool.
Yeah.
Yeah, so with the free variables, that's just something for the type checker basically is just like check if there are any free variables. And so currently I don't have any type checker checking if they're free variables, and if there are, just not allowing the thing to execute, right? That's a pretty easy, it's a very small addition actually, because basically all I have to do is add a precondition where it's like, okay, check if there are free variables. If there are any free variables, just don't run the program, basically.
Well, do we care? I mean, we just rather run the program, or?
Yeah, I don't know, quite frankly. I'm not like, what's the danger of having a free variable? I'm not really sure, but
Well, we'll catch some mistakes.
Yeah. Well, yeah.
I mean, you can also plug some kind of system process to this free variable.
Okay.
You know what I mean? It's a standard output. If X is standard output, you say, okay, it's not free, it's standard output.
Yeah, right. Yeah, so I mean, yeah, we could designate some variables maybe and just have them work like that, and then not consider them free variables, because I mean, kind of the beauty and the pain of K framework is you're literally defining every single thing from scratch, or at least that's the way that I'm approaching it. I'm literally not using any built-in tools whatsoever to do the actual language design. They do have a built-in substitution, but I found that it was less than desirable, so I have actually defined my own substitution to try and actually mimic what rholang is actually doing. Yeah, so let's look at another example here. So we did so we had a race condition. There were free variables there, so maybe let's get rid of the free variables. So the way that we get rid of free variables is, well, we just declare it as an unforgeable name, basically, right? So instead of just running this in the curly braces, which would run just fine, because I don't stop the program from running if it has free variables. But so that it doesn't have free variables, we'll just declare it as some new unforgeable name. So we have send on this channel X, and so now I'm sending 2 messages. It works basically the same as sending 1. And I have a receive on channel X as well. And I'm listening for 2 things. And so you'll notice my syntax is a little bit weird, but this is the way that I can consistently distinguish between process and name variables. It was an issue for a long time, and then I basically just figured, okay, I'll just throw a slash in there, and then all of a sudden now everything works perfectly. So, okay, fine. It's a little bit clunky, but I don't really mind so much. But either way, so when I say something like @/y, that just tells me that /y is a name or a process variable. And so I can use it in process context. Like I can add 1 to it, But this y here, just as a variable, is a name variable. So I'll have to evaluate it before I can do anything with it in a process context.
So you can have like the same name for a variable.
Yeah,
right?
yeah.
One with a backslash.
Right. Yep. Yeah, so I mean that was I don't know, the easiest workaround, I guess, because if I just tried to put you know, like an @y and a y here, it would get confused and not know if when I call y here if it was supposed to be a name or a process, and when I call $y here it wouldn't know if y was supposed to be a name or a process. So there were just all sorts of parsing issues when I left it like that. But this is a pretty easy mapping to just take all your process variables and put a slash in front of them. So
yeah.
okay, cool. So this will be a little more interesting, I guess. Maybe not so much more interesting than what we've seen before. But either way, we have this unforgeable name being declared here. So we shouldn't have any free variables here. At least maybe we should go through it and see that there shouldn't be any free variables. So X would definitely be a free variable here, but we've bound it with the new construct. So it's no longer a free variable. No free variables from that stuff. Here, well, X again, but it's already bound, so we're okay there. The /y and the $y would be free variables, but they're being bound by the fact that we're listening for those names here. So it shouldn't be any free variables, but we'll see what the program tells us. So this is okay. See what happens. So we only had one send and one receive here, so there shouldn't be any non-deterministic behavior. So we should only have one result when we execute this program. And yes, it always takes this long. It's a good exercise in patience, I guess. I don't know. That's what I'm telling myself, at least. Okay, so cool. Let's talk about what happened here. So basically what happened was, so we declared this name X as an unforgeable name. You can see, so let's just look back up here. So there were no unforgeable names in any of our previous programs. So this location counter just stayed at 1. As we declare unforgeable names, that index increases. So here we declared 1 unforgeable name. So we're no longer at 0, we're at 1. And basically what it's going to do is, in the scope of this new statement, it's just going to find all the occurrences of X, all the free occurrences of X, and substitute, you know, unforgeable 0, whatever location is available when that name is declared. There we go. So either way, that's why this location counter has now increased, because we did define an unforgeable name. And so what happened was we sent this message 41, true on this channel unforgeable 0 or whatever. And we also listened on exactly that same channel. So of course there should be a COM event for this process variable /y and this name variable y. With the process variable, we wanted to add 1 to it. So just going based off of what we see here. So we had 41 was the first message. So that should be the thing that's being bound to our process variable /y. So we should have a 41 plus 1. So we should get a 42. And that's where this 42 is coming from in this KCell. It's an integer. They're ground terms. We don't do anything further with an integer. So it just stays. And then the other part of this is we had a true message, which was being bound to this name variable y. And that was going to, you know, go for further processing in this not $y. So basically we should see not true, or in other words, false, and that ends up here. It's a Boolean, so it's a ground term. It doesn't do anything any further. So this is our final state, is with 42 in one of these thread cells and with false in the other thread cell. And so you can see that when we do this parallel composition here, right, because we were just taking whatever our process variable /y plus 1 was, which was 42. And we're running that in parallel with not *y, which was false. And so what we see is that we actually have two separate thread cells that are containing each part of that parallel composition. And then the same stuff here. So we didn't have any free variables, so it's telling me it's an empty set. That's what the dot set notation is telling me. And then also this stuff, for some sort of alpha equivalence, but we don't exactly need it here. But you can see it's kind of indexing all of these variables as it goes, all of the bound variables. So indexing that X as bound name. So I even distinguish between name and process variables in my alpha or my De Bruijn index. So here I have bound n, so I know that it's a name, bound n, so the 0, that's the same 1. Here it's telling me at bound p 1, so this is a bound process, and this one was a bound name, and then I can go ahead and make sure that everything is, kind of worked correctly, but I've done pretty significant testing, so I think this is still working. Yeah, does that make sense? Any questions or anything like that?
Sounds good.
And you only need this next location to remember, right?
Yeah. This is just for when I'm declaring several names, so that I always declare a unique name and don't shadow previous names that have been declared already. Yeah. So yeah. Go ahead, Jim.
I don't understand why you would bind to the name, use Y both as the name and the value, rather than just bind the first element to Z instead.
Oh, you're talking about this?
Yeah, why not just say Z instead of name of Y?
Yeah, and you absolutely could, right? And so the only point that I'm trying to make here is that I'm trying to do it just like the co-op rholang is currently. So in co-op rholang, you can just as easily define Y as a name and a process variable in exactly the same statement, and then run your code like that. So I just wanted to mimic exactly what they've been doing.
Okay, seems a little scary.
Well, yeah, that's why I put the slash in front, right? Anytime it sees a slash in front, it knows that this /y is something very different than just the Y. But that was kind of the issue with the built-in substitution, is that it didn't recognize them as different, and it started, substituting names here for this process variable, and things got bad really quick.
Okay, let's put it on robot.
Yeah, absolutely. All right, cool. Okay, so we saw the new name declarations. So I'll show you some stuff with input guards as well. So here we're going to send several messages to the same channel. So here I have a send on channel X of 41 and some other thing. Send on channel X with 40 and some other thing. And then I'm listening for two different messages. So good. Both of these sends had two messages associated with them. And so what I'm going to do is, with the first message that I get, I'm going to check that it's greater than 40. And if it's not greater than 40, I'll just ignore it completely. So what should happen is this message should be ignored. Even though there are two sends and one listen, there won't be a race condition here, because I'm just simply going to ignore this message. It doesn't pass my input guard condition here. And so either way, once I get a message on this channel X, once I have a comm, basically what it's going to do is just take whatever that value was for Y. So that was the first value. So in this case, it should be 41. It's going to add 1 to it, so I should end up with 42, and then I should end up with a send on 42, and I should send whatever was the second coordinate there. So it should be a star A. So I'll just show you what happens here. But of course,
Yeah.
A should be some unforgeable name.
rholang doesn't have a way where you could do a guard like
Not yet.
not
Yeah.
than 40 range.
Yeah. Yeah. So some I think some aspects so I've gotten some things to work before they've gotten them to work, but certainly they have a lot more things working than I do currently. But this is something that I got to work, and I was actually really happy that this worked, and I'd like to show you guys the code for that if you're interested in it. So let's go ahead and run that. So this is guard 1. Okay. All right. Lots of fun stuff going on here. Oh, so first thing to note is that okay, great. This all looks really good. This De Bruijn indexing, it looks really good up until this point where you see this hash De Bruijn blah 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 some stuff. There's some maps there. I just haven't fully finished defining this De Bruijn indexing for absolutely everything. So here's a case where it's not defined for it yet. So it must be when I'm listening for multiple names and I have an input guard, it's not defined yet. So this is still something that I'm working on. But okay, let's not focus on the negative, right? Let's just see what happened with this program execution. So let's see, this is the reason why I kept these, the original here. So just looking at the original, like we said, we should have a COM event happening, right? Because we're listening and sending on the same channel. Specifically, we should only see this message 41 star A that's actually being consumed by the receive. So there should only be one result. As you see, there is only one result. That's the only one. And what we should see is, well, there should still be something corresponding to this send left over in the tuple space, so we can try and find that. The thing that corresponds to that send is this at unforgeable 0, 40 comma unforgeable 2. And how do I know that? Well, because as we go down this line defining these unforgeable names, what it's going to do is use the location, right? So X will be defined as unforgeable 0. That was my first location. A should be defined as unforgeable 1. B should be defined as unforgeable 2. And that was all of the unforgeable names that we defined. So we're left with our counter at 3 here. But either way, I should see an unforgeable 2 appearing in the second, as the second message here. And of course, a 40 as the first message. And that's exactly what we're seeing here with that particular send. It's consumable. There's 2 messages. Everything checks out. And so what should happen, like we were saying, is we should have a COM between this send and this receive. And so what happens is when that COM happens, we're going to take our first message, which was 41. We're going to add 1 to it. So we should end up with 42 as the channel. And we're going to send whatever the second thing was, which is going to be, an unforgeable, an unforgeable 1 on that channel 42. So let's see that happened. So notice we don't have anything left in the thread cell because here everything was either a send or receive at the end. We were actually able to execute it. And once a send it or a receive is executed, it just lands in the tuple space until it can form a COM event. And until that time, it just sits in the tuple space and waits. So this is what corresponds to that continuation here, right? So we had our channel was at 42. Our message was unforgeable 1, right? There's only 1 message and it's consumable. So this is the piece of the configuration that corresponds to that continuation. What questions do you guys have?
This is very clear.
Perfect. Great. All right, cool. So that's basically that. Like I said, there's still some things that I'm working on in terms of De Bruijn indexing. This being one of them. But either way, so something that I recently got working that I was very happy about was name equivalence and structural equivalence, and I did kind of a deep dive about that last week. But I just wanted to show you an example, at least, of this stuff working. So with name equivalence and structural equivalence are basically go hand in hand. One is just for names and one is for processes. But essentially what we can do at this point is take channels that are name equivalent, just like in the row calculus, and still have COM events happening over name equivalent channels. And so let's just look at the channels for a second. So the channel for this one is going to be, well, this quoted process. This process has 4 different things running in parallel. That it's a one, just an integer ground term. It's this send process, which is sending on channel 3, the process nil. It also has this nil process running in parallel, and also the string. So basically everything is a ground term except for this send, but it doesn't really make any difference. So this is the first channel that we're sending our first message on. So we're sending the message 42 comma true or 41 comma true on this channel. The second channel looks pretty similar, except it doesn't have a nil also running in parallel with it. But if you recall about parallel composition, is that nil is the unit of parallel composition. So it makes no difference if you put a nil in par with anything else. Structurally, it means the same thing. Point being that this channel 1 par, send nil on 3, par nil, par string A. This is structurally equivalent to this process that I have here. And so then these channels that I'm sending these messages on are name equivalent. And the other thing about parallel composition is it doesn't matter what order your processes are appearing in the parallel composition. So here I've just rearranged some things. So, the string A is the first one that's appearing, then the integer 1, then the send. The sends are the same. But either way, this is also structurally equivalent to both of these processes. So all 3 of these channels are name equivalent here. And so what should happen is since these channels are name equivalent, we should have COM events that can potentially happen from either of these sends and with this one receive. So we're still using consumable receives and sends, so no persistence here. So what's going to happen is basically, well, either one of these should be able to communicate with this receive. And so depending on which one it is, we'll have a different list that's output. But this list is a ground term, so it'll just get stuck in that thread cell. It won't execute any further. So we should have non-determinism here. So let's just go ahead and see what happens. So this is name. And one. Okay. All right, cool. So let's see how many results we have. So we're looking at 1. We have that OR. So we're looking at 2, and that's it. 2 results, which is exactly what we would expect, right? Because there were 2 different sends and just 1 receive. So 2 ways to reduce that. So what's happening here is, so we had a COM between the send that was sending the message 41, comma true. I'm forgetting a little bit what the continuation was supposed to be. So here's the continuation, right? Whatever the number is that we're sending, right? Because in both cases, the integer was the first message, and then some Boolean was the second message. And so we're consuming the send that was sending the message 41 and true. So we're ending up with a 42 and false, exactly what we would expect by adding 1 to 41 and putting a not in front of a true. And then this other send is just sitting in the tuple space, just waiting for a receive on that channel or some name equivalent channel. So it's basically all that happened there. We didn't declare any unforgeable names, so this counter is still at 0, and apparently we didn't have any free variables either. Okay, great. And then in this case, right, we're consuming the message -43, so we consumed this message in this case, right? So we had -43, which we then added 1 to get us to -42, and that's where that's coming from. And then we were also sending true as our second message, which we're negating and turning into false, right? It's ending up as a list up here, and so like I said, it should just get stuck in that K cell because lists don't execute any further. They're ground terms. And then we also have this other send just sitting in the tuple space in a send cell waiting for another receive. And yeah, that's basically it. Any questions about that one? Would you guys like to see some of the actual code for this stuff? What are your interests?
Yeah, I would like to see, definitely.
Okay, cool.
Do you plan to support maps?
In what way? Like rholang maps?
Yeah.
Yeah, absolutely. Yeah. I have some maps here already. Yeah, actually that's a good thing to look at. So I have maps, let's not look at that yet. I have maps defined. Sorry, I'm scrolling through this pretty quickly. But here, yeah, I have our rholang maps defined here, right? So a rholang map is basically just like a JSON object, right? It's just got the curly braces, and then we can put processes as keys or values. And so that's basically all that we're doing to define this. Yeah, and so maps are ground terms as well, right? So even if, say for example, the continuation in that last example was a map, right? It wouldn't do anything once it actually got to that map. It would just sit in that KSL. But yeah, so I have, boy, I don't even know where to start with showing all of this stuff, right? So maybe one thing that I should say, I know Jim and Tomislav have seen this before, but I'm not sure how much experience you have with this, Steve. But K-framework uses, so to define, so I'm defining what they call the syntax for the semantics, right? Because the only point of defining your syntax in K-framework is so that you can tell it how to execute programs with the rewrite rules. So what we use is kind of a BNF notation, right? So I'm basically saying like, here's some structure, and the way that I define that structure is recursively, and I'm going to use this other, type or sort or whatever you want to call it, which I've defined way above, and I'll show you that in a second. But it's basically just about terminals and non-terminals. So this proc and proc are both non-terminals. They're both non-terminals, yeah, because these can expand further, but then basically I have this terminal object, which is just like, this is a fixed thing every single time. A row key value pair is always defined as some process colon some other process, right? It's like key and then value. And then we can build up key value pairs by basically saying, a key value pair I just defined, right? It can be a process colon process. And so key value pairs, like plural, can either be 2 or more, essentially. And this is maybe a slightly clumsy way of defining it, but I've found that it works really well. So I'm just going to stick with it. And so basically it can be a single key value pair with another key value pair, which would give us 2, right? Or with a comma in between, right? So our non-terminals and our terminal. Or it can be just a leading key value pair, so like the head of a list, and then all of the rest of them, and that could be arbitrarily many, essentially. And then to turn key value pairs into a map, you just put them in curly braces, basically. So these key value pairs by themselves are not processes, but the second you put them into the curly braces, now it's a row map, and now it is a process. So an interesting thing with K-Framework is, since it has built-in features already, but you're also trying to define syntax, sometimes there are collisions with the syntax that you want to define and the built-in stuff that they already have. So in the case of just putting parentheses around some particular category, this is already a defined notion in K-Framework. So the way to circumvent that is, if it's already defined, then you can define it again, basically kind of overload it and attribute a K label to it. And then this is basically telling it to interpret this thing as this row tuple instead of as the parentheses that are already built in. So I can show you maybe a case. Let me think of a good spot where I define something with a row tuple, maybe in these auxiliary functions. Sorry, I'm jumping around a little bit, but I'm just trying to find somewhere that I actually use that.
And this will be decided by order of syntax rules, right? Right.
Yeah, by order of syntax rules. Dang it, why is it not in here? Maybe this is a bad one to choose. Yeah, okay, apparently that was a bad one to choose. All right, well, either way, anytime that I want K-Framework to interpret these parentheses around a process as specifically a row tuple, as opposed to just like putting a process in parentheses to kind of restrict the scope, I also have to put this tuple like tag on the outside. So I would write tuple in parentheses, whatever my row tuple is, and then it will automatically know this is a row tuple, and I interpret this in a very particular way, basically.
Sorry, so you're using a row tuple only on some places, or?
Yeah, right. So sometimes, yeah, go ahead.
Is this a substitution, or?
Is it a substitution? So I think about it kind of like in Scala, where you're defining a class or an object, and you want to define a method that already has a name, so you can just override that method name. It's kind of a similar thing, right? It's like I have the same syntax to mean two different things. So the way that I do that is I just have this extra tag there, so it knows to interpret it one way as opposed to the other.
I guess the other thing I was wondering is, when you're defining the syntax of the map, you didn't define the spacing. I guess there's built-in rules for that.
Yeah. So any amount of white spacing or enters is totally fine. The parser just doesn't even worry about it, which is very nice, right? Because once I define these categories or types or sorts or whatever you want to call them, those are all basically synonymous. It generates the parser for you, right? So you don't even have to worry about telling it, oh, don't worry about this white space or this enter or something in these particular spots. Well, so one thing that I can say, okay, great, there's a good example here is, so for set, the way that I've defined it here, and now it doesn't really matter how one defines it, but the way that I defined it here is it's three terminals. So you have to have this keyword of set. Then there can be any amount of white space between that and this open parenthesis, which is the second terminal. and then just whatever number of processes, and then this closed parenthesis, which is the third terminal, as opposed to something like unforgeable. So unforgeable only has two terminals. So the first one is unforgeable, no space with in a parenthesis, an open paren, and then some integer, and then this closed paren, right? So these are very different, because if I were to type the word unforgeable, put a space there, and then an open parenthesis, it wouldn't know what that is supposed to be, right? Whereas if I put set and like 80 spaces, it would be totally fine, and it would be able to interpret it correctly.
Suppose you wanted to require that the set had no space, and then
yeah, so it would be pretty easy. So these quotes are just telling it what the terminals are, and I can just go ahead and get rid of those.
Yeah.
Right, I could do something like that basically.
But if you had suppose for the row KD pair, you wanted to not have a space before the colon.
Yeah, that I am not 100% sure how. I can definitely tell it to space it, right, just by putting a space here. I'm not sure how to say it absolutely cannot have a space there. But I also haven't found an example where I would absolutely need it to not have a space in between the terminal and non-terminal. So one thing that I can show you is just so some of these. So yeah, okay, we can look at the processes. So one nice thing that it does is it has so syntax precedence. So basically, so we have several syntactic constructs that could be interpreted, several different ways. Having precedence rules helps it parse things without putting parentheses, 10 million parentheses basically, just to enforce the parsing rules. So the way that K-framework deals with that is basically like, okay, here I'm defining the process syntactic category. And it's built up by a lot of different things. But basically what I want it to do is ensure that all of my new constructs have highest order precedence. Then my ground constructs have the next high order precedence, and collections and process variables all have the same precedence as the ground terms, and that's with the vertical bars instead of with these greater than signs. And then variable reference have the next highest precedence, and so on and so forth. But basically, so all of these things are pieces that make up this process syntactic category. And not only that, I'm also telling it order of precedence for parsing the syntax. So this is this order of precedence is like a nice built-in feature for the parser, just to make it a little bit better, so I don't have to put so many parentheses on everything. But yeah, so defining just process variables here, right? Just put in front. Of course, when you are in a string, you have to put one slash before you put the one that will actually appear. Let's see some other stuff here. Yeah, so I can show you. I'll show you some of the configuration.
Can I just ask you about this overloaded tuple?
Yeah.
What is the syntax that overloads?
Yeah. So K has okay, everything that you define in K, right? So all of like a process, a bound process, arithmetic expression, Boolean expression, like all of these things, just by virtue of being defined as a syntactic category, automatically are put into the syntactic category K. So there's like a main category that everything falls under, and that category is called K. And basically it just means that all of these things are computation elements. And so all of these things that fall into the k-syntactic category, which is everything that you define, there's a parentheses on k objects already. And so if so they have built-in parentheses, right? Any k object you can put parentheses around it, and that's well-defined syntax. But I wanted to specifically be able to put parentheses around processes and then distinguish it from a process, right? Because it's now a row tuple, right?
Yep. Okay. I was.
Yeah.
Sorry.
Yeah. No. I was just going to say there's this attribute called poly, which I can show you an example of. Let's go way up to the top of this. Sorry, I'm scrolling through a lot of stuff. So here, there's an attribute for something like this. So here I'm defining a function, as you can tell by that keyword function, right? And then I also have it that it's polymorphic in the 0th, which is this argument, and the 3rd argument, which is this argument. And so basically all that's going to say is, well, this thing is a function, right? It's going to execute until it can't possibly execute anymore. And also what happens is whatever category or whatever type of process I have here, that's also the same type as the result, right? So whatever appears here is going to be a process, sure, but there are many, many, many types of processes. Like, is it a new, or is it a row map, or like, all of this different stuff. Whatever I put here, that type will be reflected as the result type. So this is like a really nice way to do that. And so the parentheses on the K objects are exactly that. They're polymorphic, and so they're going to take in anything like a process, for example. But if I put parentheses around a process and don't tell it that it's a tuple now, it thinks it's still just a regular process and not anything more finely grained.
Okay, thanks.
Yeah.
I was thinking that you're overloading your existing, your already defined some kind of expression, but you're overloading like from K framework directly.
Yeah, exactly. Yeah, built-in construct. Yep.
Yeah. Thanks.
Yeah, absolutely. So let's see. Yeah, so here is the configuration, right? So the configuration in K framework, this holds the entire state of the program, just all of the important information regarding your program. And I remember I tried to compile it, got a ton of errors. I realized what my errors were coming from because I was changing names of cells here, and you just can't change the name of a cell here and then not change it elsewhere, which is exactly what I did. But either way, so I got some errors, but that's okay. But basically, yeah, so we have, so everything in the configuration is stored in this top cell. This is basically just so it's all self-contained, right? So the top cell contains everything else until it sees this /t. But either way, so within that top cell, that's the important stuff. So we have, what I was calling the threads, and here is now being called the activity. It doesn't really matter what you call any of it, but either way, we have some cell which is going to hold several subcells. And how do we know it's several subcells? Well, because it has this multiplicity star. This is like the clean star. Multiplicity star means there can either be 0 of them or more, right? So 0, 1, 2, however many you want. So you notice that sometimes that K cell was, or the thread cell was empty, and it basically just said like dot thread cell bag or something like that. When you define something with a multiplicity star, like I said, there can be many of them, but they're treated as a multiset. So you can have many of exactly the same thing appearing. And that's exactly what we want for something like the tuple space, because we want to be able to make multiple sends to exactly the same channel with exactly the same messages and still have it represented in the tuple space. So if I send, identical messages, like 5 identical messages to the same channel, I want there to be 5 comm events if I'm listening on that channel, the appropriate number of times. I don't want it to only have one comm event. So it has to be a multi-set. It can't possibly be a set. So that's what these cells are doing. All of these cells are multi-sets when you declare them with multiplicity star. Yeah, what's up?
Can you say directly on K multiplicity star?
What do you mean directly in K?
On a K cell, because now you have a task just around the K cell.
Yeah. Yeah. Oh. So can I say multiplicity star here?
Yeah, exactly.
So I'm not sure. You might be able to, but I'll tell you what the issue is. If I were to try and do something like, okay, get rid of that, and now you see I have 2 K cells, it definitely will not allow me to do that. So I can't have 2 explicit K cells. So I might be able to do the multiplicity star directly in the K cell. The reason that it is not, the reason that it's not that way currently is because I was originally experimenting with environments and treating new name declarations with environments, and I've now since abandoned that model for like a pure substitution model, and so now there's not really any reason to have this one cell within another cell that has a multiplicity star. But before I did have more than one cell in here, and that's why I had it. Yeah.
Okay. And now you can easily extend and add something inside the task.
Right. Yep. Yeah. Exactly. Yeah. So I can put more cells in the task cell if I wanted to. I just don't know if anything needs to be added currently. And then the tuple space cell holds the send cell. Send cell can hold several send cells because it has multiplicity star, right? So it could be 0 or it could be more. And basically what this is going to hold is just information about the channel that I'm sending on, the message, how many messages there are, which for some reason I called tuple, several months ago. And whether or not it's consumable, basically, right? Like, is it supposed to persist after a comm event, or is it supposed to be consumed after a comm event? So this dot K, so all of the syntactic categories in K have a unit notation, like an empty thing. So this is just, well, there's nothing there, that nothing is of type K, basically. But essentially, this is just like a placeholder until I actually populate it with the information that I actually want there. Like here, I'll put a name, of course, because it's going to be a channel. Here, I'll put a process or multiple processes. Here, I'm going to put an integer because it's just telling me how many processes there are. And here I'll also put an integer, but it's either 0 or 1, just, for if the message is consumable or if it's persistent. Basically the same thing with the receives, right? I can have as many of them as I want, 0 or more. I record the channel, which is just a name. I record the variables that I'm binding. So like if I'm listening for a name variable A and a process variable B or something along those lines, I'll record that information here. I also record the number independently just because then it makes it really easy to check. If I have 12 messages here and I have 12 things that I'm listening for, I can automatically see if those will match. And if they do, I can go ahead and perform that reduction. This R type is just about, again, if it's persistent or consumable. So there's 3 different types that a receive can have. So it can be just linear, so consumable, and it consumes the send with it. It can be peak, which is it is consumed in the comm event, but the message or the send is not consumed. Or it can be persistent, where it consumes the send, but it itself is not consumed. Yeah, and then other than that, I basically just have this counter, which I said is for the name declaration. So when I'm declaring unforgeable names, just to make them unique every time I declare them. So one thing I didn't mention about this K cell is it has this special variable in it. So the K cell has this special variable, which is this $ PGM. And that's basically saying whatever it parses as the program in terms of the K abstract syntax tree. That thing is what will be placed here. And not only that, but I want to check that it has type process. So I only want processes to be valid programs. And so this is, of course, by my scheme of what a process is, because here I'm saying that a process is something with free variables. As you saw, we had programs with free variables running. So processes can have free variables. But, the thing that I was saying was really easy to do is I can basically just, prepend this computation to check for free variables. If the set of free variables is empty, then okay, just get rid of that error message and go ahead and parse the program properly. But if it's not empty, then, well, you got free variables and don't run the program, essentially. So that's all that's going on there. Yeah, so then in the original cell, right, this is just like take the parsed program and put it into this cell, right? So just display what it was that I wanted you to parse in the first place, right? So I just capture that with this $ PGM business. The free variables.
Is this really parsed, or just because you're not constrained this to proc, right?
Yeah, so this one I'm not constraining to proc, only because I've already constrained this one to proc. So basically all of them by virtue have to be constrained to process,
okay.
right?
Okay.
Yeah. Cool. Yeah. So so I'm not even sure if calling this $ PGM, so I call it, 4 times here in this configuration. I'm not sure if it individually turns it into the abstract syntax tree 4 different times, or if it just does it once and then records it and then populates every time it sees the $ PGM. I'm actually not really sure, because up until about 2 weeks ago, I didn't have any of these cells. So this is something I'm recently starting to experiment with.
Yeah, this is an interesting question.
Yeah, I'm not sure. Because you could conceivably, want to call that thing several different times in multiple cells. I don't know if it parses it every single time anew. But yeah, so then we have a free variables function, which is defined in this definition here, which is quite long and probably will not go through all of this stuff. But either way, so I have two separate types of free variable or variable functions, and basically one of them is going to take all of the free variables or the variables, depending on which one you're calling. It's either going to be FV or V, and it will take all of those variables with their type, so whether they're a process variable or a name variable, and that's what I'm calling kind sets. So it tells you what kind of variable it is, but I also have unkind sets. So this one is doing exactly the same stuff, but not typing them as it's going through, essentially. And this is useful in one context, and this one's useful in another context, so I just kept both of them. But either way, so this one I'm calling the kind variable, which is why, I think the last one was an empty, but either way, this is why it was telling me, here I had a free variable X, which was in fact a name variable.
This what you showed is definition of this free variable function.
It's a long definition, but it's in here in this namevar.k. All of this stuff is on GitHub too, so yeah, it's in namevar.k.
But this is just the syntax rules, right? This is not the definition.
Well, yeah. So these are the syntax rules, right? So I'm just defining, FV on some arguments. The argument is basically just like anything that you could conceivably have as an argument in this free variable function as you're kind of like, unfolding all of the structure of your term. Yeah, and it's a function, right? So I'm just declaring this FB as syntax so that I can make it a function. And basically, it's going to take an argument of any of these types, and it's going to give back a set, right? So set being the built-in kind of set, which is why we were seeing things like.
But where is the exact definition?
Oh yeah, it's lower. Yeah, so here.
Oh, it's just okay.
Yeah, so for example, right, like for variables, if I want to talk about just variables, not bound or free or anything, if it's a ground term, well, no ground terms don't have variables, so this is just the empty set. But if it's okay, I don't really want to talk about bound process, but for a process variable. If I have a process variable and I want to compute the set of variables, well, it's just exactly that. And, if I'm including the kind with it, then it's a process. And if I'm not, well, it's just that thing.
Yeah, I see.
Yeah, but this goes on and on and on.
Yeah. Okay. I see. You're correcting to a set, so you can structurally compare it.
That's right. Yeah, exactly. Yeah, and so it gets so with the variables, it's fine. This is not terribly difficult, right? Because I'm just trying to find occurrences of variables. It's the free variables that are a little bit tricky because with the free variables now we have to account for binding phenomena, right? So like with receives, right? So I have some names that I'm listening for. Oh, excuse me. And all of these names are now bound names. So I'm going to have to go ahead and subtract those names basically. So there's like a slight difference, but I'm going to have to subtract those names from the set of free variables in this continuation. And then I'll go ahead and union those together, right? So this is like a set difference. And here's an instance of where I'm using the built-in parentheses. So this is the built-in parentheses, right? Because I didn't tell it that it was a tuple. Be a little bit weird for this to be a tuple. But either way, so I'm using the built-in parentheses, right? Just to basically say like, okay, this set difference takes precedence over the union that's there because I don't think there's a precedence defined between them. Yeah, but okay, that's basically all that's happening there. Yeah, and then the only other thing is I have this de Bruunified cell, which is just capturing, replacing all of the bound variables with their de Bruin index, essentially. And so that's it for the configuration, right? So all it's keeping track of is, the stuff that's in par, right, in this kind of activity or thread cell, whatever it's being called, it doesn't really matter. And each thing in par is going to appear in a K cell where computations will be performed concurrently. And then we also have the tuple space cell, which has all of the send cells and all of the receive cells, and then basically things just for bookkeeping. Yeah, so let me show you, this stuff is not too important. Yeah, so this, I think you guys have definitely seen this before, but either way, if so after we separate everything in par, right? So if I see parallel composition, basically what I'm going to do is check that the first thing that I'm writing here, so this process P, I'm going to check that it itself is not several processes paired together. So I want kind of like an atomic thing from the view of par. And I'm going to pluck off just that single process by itself, put it into its own thread cell, and then basically forget about the head of that list and just keep the rest of the par. And then do that over and over until it's all individual processes in K cells. Once I have individual processes in K cells, it's going to be send, or a receive, and then they're processed further into the tuple space, or they just sit there in the K cell because of ground terms. So that's basically all that's happening with those. So with the send cells, we're going to take the channel from the send. We're going to take the messages that we're sending, how many of them there are, and whether or not it's a consumable send. With receives, more or less the same stuff is happening, right? I take the channel, what variables I'm listening for, how many of them there are, whether or not it's persistent, this guard thing. So if I see a statement that's, if some Boolean expression, then that Boolean expression is my input guard. If there is no input guard, then this by default just returns the value true, and then there's nothing to overcome with the guard. And then also the continuation. And basically exactly the same thing here, except I did something weird with the order there, but that's okay. And so, okay, this is the part that I really wanted to show you. So with these COM events, right? So what we're looking for is we're looking for send and receive that are on name equivalent channels that have the same number of messages. And then also, even more specifically, those messages need to match. And that's something that I'm still working on. So at first there was a structural type system that was being used to determine whether or not two things matched. I'm thinking that I can get around the structural type system and the type inclusion predicate, because I don't think they're necessary. I don't think they add much to anything, and I'm pretty sure I can get around it. So I'm currently defining this predicate called match, which basically does both at the same time instead of a structural type system independently of this type inclusion predicate and then having to balance all of that. So this, I've commented it out because it's not 100% done, so I didn't want to include it just yet. But basically what's going to happen, right, is I have some receive up to here, some send, and so in this case, right, I'm talking about the case where they're both linear, right, like linear receive. So if there's a communication event and we process this receive, well, it'll be consumed, so we're going to pull it out of the tuple space if that happens. Same thing with the send. This is also a consumable send because of the 0 here. So if there's a COM event, we'll pull it out of the tuple space, and so that's being captured by this arrow.bag on both of them. And so basically all that's saying is that if this rule proceeds, right, if this rewrite rule occurs, then part of that rewrite rule is to delete this receive, and deleting that receive is basically just by saying rewriting it to, well, nothing, and delete this send by rewriting it to nothing as well. And so if that happens, right, if this send and receive do actually COM with one another, then what we're going to do is spawn a new K cell that is going to contain the substituted continuation, right? So here's my continuation, some process P. That continuation, so it's here, right? What we need to do is take whatever messages we're sending, so that's the Q process here, and we're going to need to substitute that message in for my binding variables, which are Y. So here's that notation, right? So I'm going to substitute at Q for Y in the process P. So that's what that notation means. And so this is the substitution function that I've defined. It's defined here in this definition, sub.k. And that only happens, right, if we have two conditions satisfied. So one of those conditions is that the input guard is satisfied, right? So whatever this input guard is, it's some Boolean expression For example, we saw something that was like star y is greater than 40 or something along those lines. So what I need to do is see if the message that I'm going to substitute in, right, check if it satisfies the input guard. So the way that I check if it satisfies the input guard is I take the input guard and I substitute the messages that will ultimately be substituted for the variables into the input guard. And then if it comes out as true, well, great, we satisfied that input guard, so that will pass, and all is good. And then the only other thing that we need to check is that the channels are name equivalent, and that's what this predicate is checking. Right, so there's two requirements here. So one is that we pass the input guard. The other is that the channels are name equivalent.
What will happen first? This name checking or substitution?
I'm not sure. I think probably the substitution, the input guard stuff happens first, but I'm actually not sure. When it comes to and bool, I don't think that it's strict in either argument. So I think it might even just do them at the same time, actually. But I'm not 100% sure about that. What I would like to happen first is that we check if it's even going to match. If it's going to match, then we'll check. Well, I guess, yeah, I'm not really sure what the proper order is, right? Like, should I check name equivalents of channels first, and then if the messages are going to match, and then if the input guard is satisfied? I really don't know what order to check things in, but yeah.
I like that you're using the substitution function in two different places, but the same function.
Right? Yeah, right.
For continuation and for guard.
Yeah, exactly. So yeah, I thought this was really cool. I wasn't sure how all of that was going to work, and at first when I started trying it, I think I had maybe neglected, pretty naively neglected to actually define it for Boolean expressions, which of course I need the last argument here to be a Boolean expression. And that's when I started getting all of these error messages about SMT lib translation and all of this stuff. And yeah, but either way, once you actually define your function for the arguments you're calling it on, everything seems to work. So that's really nice.
Yeah, that's cool. And this substitution, this second call of substitution, sorry.
Yeah.
Is this return a proc, like a process, or specific type of Boolean?
Yeah. So the substitution function. So we're calling it on to name. So here's the actual version that we're using. And so what it's going to do is whatever type this process has, so in that case, it would be a Boolean expression, its output type will also be a Boolean expression.
Oh, not any process, but
yeah, specifically a Boolean expression. Yeah.
And in your example, you are calling this with B, and B is
Boolean expression.
This expression, Boolean expression. This is guard expression. It must be Boolean.
Yeah, right, exactly. Because we can go up to the Boolean expression stuff, right? I mean, it's exactly what you would expect it to be. So Boolean expressions are anything of this form, and so the process variables and evals have to be included in here so that I can do things like an input guard for star y greater than 40 or something along those lines. So I have to include these as valid Boolean expressions. But then basically once you have that stuff, it's like, okay, they can be strings, or maybe some comparison of arithmetic expressions, or maybe some match statement, or name or structural equivalence statement, or just some regular, Boolean statement, like, not some Boolean expression, or, and two of them, or two of them, something along those lines. Yeah, so it can be anything of that form, right? So as complicated as you want it to be.
Yeah. So you can say if and just say some string.
Yeah, you could, but it would never pass, right? Because we're going to substitute into a string. When I substitute into a string, clearly I get just the string back, but it will never be equal to true. So there's no way for that to pass, right? If you were to say like, if just strictly a string, like it would parse, but it would just foil your entire program, I guess.
I see. And what is the reason to have a string?
Oh yeah, just so I can use it for concatenation and that sort of stuff. So yeah, why did I want a string? So I wanted a string. Why did I want a string? Well, now I'm not actually sure why I wanted a string. I wanted a string here definitely because I wanted to concatenate. Yeah, maybe I don't even need strings here.
Okay, thanks.
Maybe just take that out. Wrong ones. Okay. All right. Either way. So let's see. Oh yeah, and the other thing that I wanted to show you was so that was just for when I have one thing that I'm listening for and one message that I'm sending, right? So like monadic stuff. If I have multiple things that I'm listening for and multiple messages, now this is 2 or more, I don't have a good way of just quoting multiple messages, or at least I can't just throw an @ sign in front of several messages and have it do what I want, but I can define a function which will do that for me, basically, right? So that's what this quotes Q function is doing. So this is taking, several processes, like say like 4, separated by commas, and then what it's going to do is just drop a quote in front of each one of them, right? So it'll be like at whatever the first process is, comma, at whatever the second process is, so on and so forth. So what this is going to do is quote every individual thing, and then one by one from the head of the list substitute in for whatever these names are here, right? So the point of that is I keep the order that things are written in, which is exactly what I want. The first variable that I'm listening for is going to correspond to the first message that I'm sending. The second one will correspond to the second, and so on and so forth. And this substitution function substitutes in exactly that way, right? Like it'll take the first thing in a list and the first thing in a list and substitute it like that, and then just move down the list, basically. But the input guard stuff works exactly the same way, right? I just want to go ahead and substitute all of the messages, quoted messages in for the variables that I'm listening for into that input guard, and then just test and see if it's equal to true. If it is, it passes. If not, we fail this requirement, and so the comm doesn't happen. And then also checking name equivalence, and then ultimately checking, if the 2 things match. But right now, I'm not quite there.
I remember that before you had some kind of way to match the number of names and number of processes in send and receive.
Yeah, and it still does, because basically what it's saying here is, so I'm listening for n things, and I have to have n messages to match. But I guess for me, the point of this is, so let's say, like, super easy example, I'm listening for a concrete process, and that thing is, so I'm listening for at 1, right? The integer 1. The only way that I'm going to get something to match with that is if I'm also sending the message 1. That's the only thing that's going to match with that. Let's say I send 2. If I send 2, well, technically it doesn't match with 1, but what's going to happen is my substitution function will try to compute it, and it just won't really do much of anything. It'll just kind of get stuck. And it'll say, I'm trying to substitute 2 for 1, and I'm just not really sure how to do it because I didn't define it. However, what I want to do is also add this this match thing here, and so then if it fails the match thing, it'll just give me a failure and move on instead of just being like, oh, I got stuck, I don't really know what to do.
Oh, I see.
Yeah. Yeah, that's pretty much it. I mean, all of the other stuff is just kind of like, you know, this repeated, right? Because this was strictly for linear listens and linear sends, so both being consumed. But then, of course, I have basically the same rules for persistent listen and consumable send. The only difference being that this listen is not consumed from the tuple space, and the send is, you know, and then so on and so forth. Those different variations. Yeah, so that's pretty much all there is to show, I guess. I mean, you know, obviously there's tons of code in all four of these definitions as well, and that doesn't even get into the structural equivalence stuff, but that's also there. And like I said, everything is on GitHub if you really want to look deeper into this stuff. But
I
yeah,
missed part of it.
Yeah.
So I watched it in the recording. Did you go over how it evaluates a simple thing like the y+1?
Oh, yeah. So something like that. So basically, what it's going to do, right? So that y+1 was a continuation. So let's just say there was only one message that we were sending and listening for only one message. Yeah, the y+1 was in the continuation, right? So we track the continuation here. I'm just calling it P, and then also type checking it that it's a process. So I mean, it wouldn't end up there if it wasn't, but it's okay to be a little more safe. But either way, that it's a process. And so what I'm going to do is, so after we know that the COM event will go through to actually process that continuation, that is that addition, what's going to happen is, okay, we'll consume the receive cell. So that's kind of captured here in this receive cell arrow dot bag. This is basically just saying delete the receive from the multi-set of receives. And this send is also consumed, so we'll delete the send from that multi-set of send cells. And we'll also create a new cell. We'll spawn a new cell. It's going to be a computation cell. And basically what it's going to do is take the continuation, which was that y+1, and we're going to substitute whatever our message was. You know, we quoted, of course, so we're doing a name substituted with a name. So we quote our message, which was, you know, maybe it was 41 or something. So we're going to do like an @41 here. We're going to substitute that for whatever our name variable was. And I think it was just Y. And so if I substitute @41 for Y, well, it just turns Y into @41 basically. And then in the continuation, it was like a star Y+1 or something along those lines, right? So I guess maybe I could write something like, so we're doing something like substituting @41 for Y in the process that looks like star Y+1, right? And so basically what's going to happen is, well, when I see this star Y, I know I can substitute for the star Y, or I can just substitute for the Y. I can either substitute a process for star Y or a name for Y. Here I'm substituting a name. So basically in one step that would go to star @41 +1. But then I have some rules later on that basically tell me that star @ is, they just annihilate one another. So the second you see a star and an @ in succession like that, you can just go ahead and delete both of them. So that'll go ahead and just reduce to a 41 +1, which of course then will just reduce to a 42. And that's how we ultimately end up with that 42.
So the plus is built-in rule.
Sort of. So the plus is technically something I've defined, and I define it here. It only makes sense between two integers, And if it's between two integers, which it only makes sense between two integers, then it's defined as the built-in integer addition that is in K-framework already. Right. So why is this necessary? Well, because I can technically add any two arithmetic expressions, right? But I don't know how to evaluate it until each of those arithmetic expressions have been reduced to integers. And so one thing that I have, which is maybe a little bit weird, but it makes sense for concatenation, is I have strings that are can be arithmetic expressions. So technically, I could write something like, you know, I don't know, a string +3, and that will parse because syntactically it's correct. But it doesn't really mean anything, and no computation is going to happen. It'll just sit in a K cell as string a +3 and not do anything.
Thank you.
Yeah. That makes sense? That's what you're asking?
Yeah.
Cool. Oh, I shouldn't have done that.
Yeah, this looks very nice.
Yeah, thanks, man.
So, do you have an account on Robot?
I do not. No.
Okay, I guess we need to make an account for you.
Yeah, absolutely. Yeah, and I'm sure there's a good way. So with is Robot executing everything in rholang right now?
No.
No. Okay.
The eval colon evaluates the argument.
Yeah. Okay. Okay.
We can make a K eval.
Yeah. Cool. All right. Yeah, that would be awesome. Yeah, the only thing that I'm thinking is because I have some weird syntactic things. So one that's come up several times is distinction between process and name variables. So we'd have to accommodate for that somehow. And then the only other one that I had an issue with was the match cases, because they want to use notation that's exactly the same as the rewrite arrow in K, but I can't use that. So I just put a colon in front of it. I don't know. Either way, everything is exactly the same.
Yeah, if we have a link to what the differences are, that's good enough.
Yeah, I mean, there's those two, and then there's like a contract invocation. I put a keyword there because it didn't like it with so methods and contract invocation have some similar syntax. Other than that, there those three differences, and that's it for the differences in the syntax, which I think is pretty good, because this syntax is technically not supposed to be exactly in line with the rholang syntax, because like I was saying at first, this is the syntax for the semantics, right? This is not really just the syntax for the programming language.
Can you show the quoted function?
Oh yeah, definitely. Yeah, this one's in the auxiliary functions. Let me just find it.
You must work with patterns, right?
Work with what?
With patterns.
Oh, everything is a pattern in K. Yeah, so I mean, so here, so there's two cases, right? Because I want it to work for processes, but the way that I've defined processes is it can be, you know, 2 comma separated processes, or it can be one at the head and then, you know, multiple at the tail, basically. And so it's a recursive function. And so if I call it on 2 processes, well, it'll just quote each and put a comma in between, exactly like you want it. If I call it on more than 2, it'll quote the first and then call quotes on the rest of it.
Oh, this is very simple.
Yeah,
so,
yeah.
So, okay. So then I have a question. How did you write substitution for?
Oh, all right. Yeah, substitution's kind of complicated. Let me see. It's got. Oh, why can't I grab that? substitution has, 500 lines of code right now, and it's not done yet. But yeah, I mean, you just go through case by case. I won't go through all of it, but we can talk about some really simple stuff. Let's not talk about the bound name stuff because that's all just for alpha.
Maybe just if you have, but yeah, you're matching for each case. Yeah. Yeah, I'm thinking when you have nested receives and you have like variables inside.
Yeah.
You must somehow match to this nesting inside.
Yeah, I know. So yeah, the new statements, receives, and the match cases, those are the ones that are real pains to work with in terms of substitution. I can show you how I've handled some receives here. Well, actually, here, I'll show you what I'm trying to do to maybe even have more robust substitution than what's currently in rholang. So here, I'm attempting to define a substitution of a receive for a receive in, a processor name. It doesn't really matter. And so basically what I'm saying is like, okay, in the case where both of them don't listen for any names, right? It's just a receive with a channel. So this can only come with like empty messages, which I'm not even sure what the point is, but I know at some point that was supposed to be included in rholang, and I don't know if it's there yet. But either way, so in this case, it's pretty simple because there are no bound variables in the case where we don't listen for anything. And so, I mean, I'm just going to substitute my name for my name and my process for my process, and that's basically it. So so you can think about it as we're like building a map, and then that map is being used to do the substitutions, which I may ultimately do it that way. It's not currently done that way. I currently just do it recursively. But what I've done so far is basically just do the substitution of A for B, right? And that's kind of captured. I'm not sure what you guys can see here, but that's captured here, right? So I take my process that I want to do the substitution into. That process, I do the name substitution first, and then I do my my process substitution afterwards. Like so this P continuation for this Q continuation. Yeah, so that's basically what I did there. And then also here, basically what I've said is I don't really care what those bound names are. I'm just going to go ahead and substitute channel for channel, continuation for continuation. I don't know if that's the right thing to do, but currently that's what I'm doing, right? So I don't know if I need to, if something needs to be done with these names that I'm listening for. I'm not really sure. I honestly couldn't think of anything to do with them because certainly these names in the first receive don't have anything to do with the names in the second receive, and vice versa. And the only thing that I could think to do was take these names and do some substitution into this continuation, but there's nothing to substitute because if these names either appear or they don't in the continuation, and substituting them in is not going to change anything. So at the time, I had convinced myself it didn't matter what names I was listening for. I was just going to substitute channels for channels and processes for processes. But I don't know if that's right. And according to our node, you can't do this anyways. So I don't know.
Okay,
but yeah,
yeah,
absolutely.
You look at this file.
Yeah, and so and then all of this stuff nests just fine because these substitution functions, they're functions. They're just going to execute until there's absolutely no more to compute. So if one of these processes in here is a receive, well then we have that nested situation that you were kind of talking about at first.
Cool.
Yeah, and for substituting like a par for a par, all I'm doing here, and maybe actually now that I'm looking at this, I probably need some sort of statement here like requires is, or rather not bool is par. A probably also, and C is not a part thing. I don't even know if that's I don't think this is absolutely necessary, because so now, after showing you guys the structural equivalence stuff, I went back and made par right associative instead of left associative, so I can work from the left side to the right side instead of vice versa. So when I write something like A par B, I'm always thinking that A is, just a single process. No, it's not like several processes paired together. And same thing with this one. So I'm thinking that C is just a single process and not, several processes paired together. So I guess technically I could write something like here with or bool. And this would be just to make 100% explicit that that's my assumption, right? Is that I even require that to be the case, that those guys can't be, pars of several processes. So I would put that requirement on both of them, but yeah. So either way, with par substitution, right? So if I'm substituting like, two processes paired together for two processes paired together, then basically what I'm going to do is substitute the first for the first, the second for the second, in that fashion. Yeah, and then requiring that to be, well, I'll have to think about it a little bit more, because I'm not sure that's how it works in rholang currently anyways. From what I remember, it works like whatever is here, whether it's par or not, it substitutes for the first thing, and then the rest substitute as nil or something like that. It's a little bit weird, but I'm not sure why that's what they went with. But either way, yeah. And so this just goes on and on with all the different possible cases that you can run into, and but the problem is that it doesn't capture things that will fail. And I tried to ask on the forum if there was a way to capture things that will fail. And was basically told that there isn't a general way to capture failure, and so that's why I started building this match predicate, which well, this check and match are things that I thought I needed, but I'm not convinced that I actually do need them anymore. So I've kind of quoted them out. There is some built-in syntax in K that basically asks for the sort of a term, but it never works the way that I want it to. So I'm just going through all these different situations, like this is what is going to do the job of the structural type system and the type inclusion predicate all at the same time. Right, is I'll just check with this match predicate, which will basically tell me, given two terms, do they match? And by match, I mean, can I, is it reasonable to kind of use those to substitute for one another, basically. Yeah, so that's pretty much it. I mean, so something really simple is like, well, if it's the same exact entry in both arguments, well, of course I can substitute, the same thing for itself. So that always works. I can always substitute any process for a process variable, and I can always substitute any process for an evaluated name variable. So all three of those situations always work. I can only substitute ground terms for one another if they are literally identical. Otherwise, it doesn't work out. So this is the thing that would give me, a false requirement when I'm checking to see if I can, substitute two for one, basically, instead of the substitution function, just getting to a point where it's like, hey, I'm trying to substitute two for one, and I'm not really sure what to do at this point. So that's more or less it. I mean, there's obviously like, 10 billion lines of code in each one of these, because it's just going through case by case, like how does this work out? But it's really nice because you only ever have to define, your base case, and then define recursively what's supposed to happen. Like, for example, here, this can be incredibly complicated terms here, and it's really nice with recursion because I can just pull off the star on the outside and say that, well, these two eval things are going to match only when the underlying names match, and then those names can be as complicated as you want, and other rules are going to cover them, basically. Yeah, so that's pretty much it. Yeah, so there's tons more stuff in the substitution, tons more stuff in this match, and it's not done. There's tons of stuff in this alpha.k definition that I didn't even show you, but this is what's doing the De Bruijn indexing. Also not done, and yeah, all of this, defining free variables and variables and that sort of stuff. Yeah, and that's pretty much it. Well, and then these auxiliary functions, which are used for the configuration and everything. But yeah, do you guys have any questions about that stuff? I realize it's almost been 2 hours at this point, but thanks for sticking around.
Yeah, thank you. That was awesome.
Oh, absolutely.
Yeah, absolutely great.
Oh, thanks. Yeah, like I said, I never really know where to start with this stuff because there's so much to talk about, and it all depends on if you're familiar or not with the layout of K framework. But the thing that I found is that it seems really complicated at first. But then it turns out that it's basically the most straightforward thing I've ever done in my life, honestly, because it's just like, okay, when this pattern matches, like rewrite it to this thing, and that's it. And you're just going through like step by step, like every single computational step is kind of laid out. It's really nice.
Yeah, and with your explanation, it looks like a completely logical, and
Oh, cool, man. Yeah, because sometimes I'm not really sure what I'm doing. So I just try things, and then they don't work, and that's okay. And then I go back to something that does work, and then try again.
Yeah, totally cool.
Yeah, awesome. I'm glad you guys enjoyed it.
Can I just ask you? I'm wondering if you want to constrain to some specific type. You really want to match on the specific constructor for this type, right?
Yeah.
For example, for if you have a proc, you want to match. Is this a par?
Yeah. Well, so there's a great way to do it, and that great way is whatever my rule is, I can then additionally say requires is proc, and if you don't need it to be any more than that. Let's say, this rule has a P in there somewhere, right? And that's the thing you absolutely want to be a proc. You just do that, right? And now you've made this requirement that this rule only applies when that thing is of type proc.
I'm thinking. This is like, is this like a function or this is not your function or this is your.
This is proc. No, this is a built-in thing. It's a predicate, right? It just returns true or false. And so what it's doing is every time I define a syntactic category like new or match case, I get one of these predicates to go with it, which then basically allows me to do that restriction to only that type. Yeah. So, and another way to do it is I can say, this has to have type proc, like in the actual definition.
And can you say this is eval or par?
Oh, absolutely. Yeah. I mean, I can just say like this, I want it to be eval, or, like in the definition, maybe I want this to be work for all processes, but specifically I want some behavior when it's an eval, so I can do something like that, right? And then like, I don't know, this reduces to 1 in that case, and then maybe if I want another case where it reduces to 2 or whatever, and this happens when it's a match or something along those lines. I can do that.
And what is the difference if you specify eval and just eval for P directly without requires?
Yeah. So then what the difference is that so eval is that so let's see, what is the difference? So the difference, I don't think there really is a difference. It's kind of just your preference, right? So like sometimes I'll just want to define it like, okay, I know this thing is going to be a process, but I want to define several different behaviors for different types of processes, right? Like in this case, I wanted to evaluate to 1 when it's an eval and 2 when it's a match for whatever reason, right? Then I can just literally copy and paste this stuff and then change this. But like I said, there's it's not I don't think there's any difference actually, because if I were to just say eval here, I can go ahead and get rid of this, and then this rule will never apply for this eval because it requires this thing to be match, and and the eval will never apply for the second case because it required it to be match. But I could also just say match here and then get rid of that.
Okay, I can see that you can have like more complicated rules when you can say this is a proc, but it requires eval or match.
Yes, exactly.
So
right.
You cannot express this just by saying.
Exactly.
That.
So I have no way, to say that this can be an eval or an arithmetic expression just by sort checking. But I can say exactly that. Like requires, is eval or bool is a arithmetic expression basically.
And you can also can you call your function, your defined function with requires?
Absolutely. So a lot of these definitions are ending up with a requires statement in them. So like for example here, right? Like I want to say that sends match sends, but they don't match other things. Well, they're going to be able to match pars. They're going to be able to match evals only because it can be, an evaluated name variable. They'll always match a process variable. So I'm going to get rid of all of those things and say, basically, if this is the case that this process here, so I have a send in some other process. If that process is not a process variable, it's not an eval, it's not a par, and it's not a send, then I'm going to return false, right? And this is if no other possible rule matches, and that's what this otherwise attribute here is capturing.
Nice.
So it'll first check any other rule that doesn't have this otherwise attribute. If I have 2 that have the otherwise attribute, I'm not sure which one it checks first, but I guess it's kind of like it always is, and it can apply any one of them at any point in time and create non-determinism. But basically I want it to say, like, if I have a send and a receive, like clearly they don't match. So I want it to go ahead and return a false in that case. But I don't want to sit here and have to be like, okay, send and receive don't match. Send and, a match don't match, and, all of that stuff, and explicitly write them all out. So that was the original point of the structural type system, but I'm pretty sure I can do exactly the same thing, 2 birds with 1 stone, basically, with just this predicate match. So I mean that's about it, unless you guys have some other questions.
Hey Isaac, it's Joshy. I actually
what's up, dude? Yeah, absolutely.
I've been listening this whole time, but just got back home, so I actually have 2 things, and maybe I'll remember some other stuff, but probably not.
Cool.
So one was I've only started watching recently, but I was listening, and I heard you mention input guards. What are input guards?
Yeah, so input guards are, let me show you an example. So are you watching now?
Yes, I am watching.
Yes. Oh, okay, cool. So input guards are like this, right? So I have a receive, which has kind of a conditional within it. So
That's
it's
what I
something.
hoped you were talking about. That's
Yeah,
awesome. Dude. You've got
yeah,
that.
yeah. Oh
Congratulations.
yeah, I got it working. Yeah, exactly. And this originally is what made me believe that I had to do an SMT translation of all of the functions that I was building before I could actually use them properly. That's not the case. You just have to actually define them for all the arguments you call them on. But yeah, this is it's working
Cool.
perfectly. So like in this particular example, we're sending 41 and some stuff and 40 and some stuff, but it's only going to come with inputs that are greater than 40 for the first message. So there's only one reduction for this thing, and it's with this send here with 41.
That's awesome. Is this the first example of when you've got something working ahead of when the main R node team got it working?
No. Well, I don't know because I have peak working. This is working.
Awesome.
Empty. I can send and receive empty messages. Like all of that stuff works for me. I'm not sure where they are with all of that.
Okay. Yeah. Cool, dude. That's awesome.
Yeah.
Way to go.
Yeah. Thanks, man.
No problem. One other thing I was going to share, this is not that high-minded, but I heard you talking for a second about integer addition versus string concatenation.
Yeah.
And I know that in the R node implementation, they use the ++ operator for string concatenation. So there's not that ambiguity there.
Right. Well, so all I was saying is the way that I've defined my arithmetic expressions is I can take any arithmetic expression and write that plus sign between. Well, I can take any two arithmetic expressions and put a plus sign in between them. And currently the way that I have it is strings are arithmetic expressions. And now I could very easily just say like, okay, string plus string is an arithmetic expression, but a string by itself is not, but I still run into that issue. But either way, so strings are arithmetic expressions the way that I've currently defined them. So I could technically write something like string A plus string B, and it would be meaningless because this addition is only defined for integers, but it would parse.
Yeah, I see. That makes a lot more sense now that I see what you had written there.
Yeah. The other thing that I could do is say like anytime I see a string with one plus sign and a string, just interpret that as string concatenation. Of course, I could do that, but that doesn't prevent the situation where it's like a string plus an integer or something along those lines.
Yeah, gotcha. Cool.
Yeah. So the excuse me, the most recent thing that I've started working on is actually including all of these like IO channels that are predefined, and then now I'm just trying to figure out how to treat these in my implementation in a way that makes sense. And the thing that brought this to my attention was this standard out acknowledgement. I saw Tomislav had asked a question about how something should execute. And I was like, wait a second, whoa, that works totally different than what I've been doing. But I think the only reason that it works totally different is because your channel you were sending on was this standard out acknowledgement channel. And so it interprets things a little bit differently. Oh, and let me test my understanding of what that is actually supposed to be. So when I say, it's always easier to just write something. So when I say something like, new out is a, row IO standard out acknowledgement channel in whatever I'm defining here, it doesn't really matter. Just for simplicity, like out bang one or something. So when I define something like, oh, actually, that's not what I want. When I define something like this with an acknowledgement channel, let's just say channel. Of course, I guess I should also say channel here, but it doesn't really matter. So when I have something like this, is this the only case where this acknowledgement business does what it's supposed to? And by that I mean, is it only when I send some message, one message with an acknowledgement channel? Is this really just kind of syntactic sugar for something like chan send one, or maybe well, it's like send nothing basically, and well, okay, maybe I'm not really sure how to ask this question that I'm asking. So what is the behavior for something like that? Maybe that's the right question to ask.
I'm thinking of that very similar to Greg's explanation of 1.1 rholang.
Yeah,
this
okay,
channel
that's what I thought
just
too.
This channel, you don't receive anything on this channel.
Yeah. Okay.
I mean, you receive mail, right?
Oh, okay. Yeah.
In a sense, this should be just like a sequence, right?
Yeah. Yeah. Right, because I know. Yeah, right, because you're usually doing this in parallel with, say, like I don't know, whatever, an underscore, and you're just listening on that channel, yeah. And then, you do something, right?
Yeah.
Okay.
Yeah, the example I used in the tutorial is when you want to print 3 outputs of text in order, where you don't want them to come with the second line first by accident or whatever. So you just need to synchronize to make sure the first thing's done before you continue.
Okay. So then I guess what I'm asking then is, so this outbang one star chan, this is really some kind of sugar for channel. Like I'm sending something here. I'm not really sure what, maybe it's nil, like you said. And that's it.
I wouldn't say it's
but after.
Oh yeah, go ahead.
I was thinking that this chain will be called after the output is written.
Yeah.
So in that sense, you need some kind of way to wait for this chain to be to wait to you can receive something in the chain.
Okay. Yeah. Oh, okay. So wait, you're saying that this needs to be read first before this channel can be sent on or something?
When you send out bang 1 star chan, you're like calling outside of the rholang world to, in this case, your operating system standard outstream, and you're saying like, print 1 and then send me an acknowledgement when you're done. And if for some reason it takes a really long time, like if some other process is hogging the output stream, don't send me that ACK until the printing was successful.
Okay. Oh, that's interesting. Yeah, so I'm not sure how to incorporate features like that into K framework yet, but I guess.
But I think it's pretty easy. So you have native I/O channels, and you can represent it. You can represent it as regular channels.
Yeah.
But you can have a list.
Yeah.
Where you can store all these processes that you received. For example, for standard out that is sending acknowledgement, you can just store this one and send acknowledgement on the channel.
Yeah.
Because you're in a sense mocking the real channel, right? Because at the end you want to see after execution, after all the COM events, in some cell you want to see this is the list of all these calls to standard output or any other native channel.
Okay.
I mean this list can be a proof what the program is called.
Okay.
I
Yeah.
want,
Yeah.
to be able to, treat any unit, what do they call it? I can't think what they call it. It's not a file descriptor, but the number, the 0, 1, 2, 3, 4. Standard in, standard out, error out, whatever else you open as a unit,
Yeah.
that would be a general capability.
Yeah, and I know there are ways to work with all of the IO stuff with K-Framework, but that's like I said, something that I haven't really fully embarked on. But it's there. I know it's there. I've worked with it a little bit. So yeah, maybe this is the time when I have to start digging a little deeper into that stuff.
Oh, you want to directly call this standard output from K?
Yeah.
Okay.
Well, or
this
at least
I was thinking more like
what it's supposed to do.
Yeah, I
okay.
thinking more along the lines of how Tomislav was saying it as like mocking this channel. Isaac, if your goal is to do formal semantics, like this stuff where you're calling standard out and standard out ACK is like the demilitarized zone between formal semantics and like real world programming,
Yeah.
like even knowing that there exists some output stream is a little bit, I don't know, it feels a little bit far from
Josh, you're breaking up.
You know what I mean? Like oh, yeah, I probably can't help that. Sorry about that.
It's okay. I think I understood what you were saying though.
Yeah, but I want to actually, use the interpreter. I want to run programs.
Yeah.
So, I mean, if you're going to mock standard out, at least I need to be able to get from the output everything that was sent to standard out.
Oh yeah, I mean K-Framework works directly with standard out, and it'll print to the terminal and everything. And there's even a way to take input from the terminal and include it into the running program execution. But that's when things start getting hairy, of course, because now you're putting information into a program that's currently running. So
for now, it's good enough to just be able to run it and get the output.
yeah, right. Yeah, and that's exactly where it's at. Yeah. Okay, cool. I'm glad I asked. I think I understand this a little bit better. Let me ask one more question though. If I wanted to send that, does that work too? Or can I only send one message with the acknowledgement channel?
I can say this will definitely not work.
Not work.
Because,
yeah, that's right. But if I do that, it now works again, right?
Yeah. It's
okay.
The definition of this system process is exactly 2 parameters.
Okay, cool. Yeah, that makes sense. Yeah, that's consistent with what I saw on our node the other day.
Maybe one way to interpret the semantics of the standard out ACK in terms of like a K-framework based interpreter would be to say that when K-framework sends a message to the operating system, when it does its IO thing, whatever IO it does, that's when it sends the ACK back. So the ACK means like, okay, I successfully relayed your message beyond the confines of K-framework. No promises about what happens next, but at least we've gotten that far.
Yeah, that's a good idea.
Yeah.
Cool.
Yeah, this is a good explanation. When you go to the boundary of rholang,
yeah, this is like when you leave the ideal world of forms, like Plato's world of forms, and enter the real world, then that's when things start getting messy.
Yeah.
Yeah, cool. All right.
Yeah, but it also would be useful, if you can just plug in, if these names are just aliases to something else.
Yeah.
If you can just say, for this system process with these parameters, when someone call this on my machine, it will work like this.
Yeah. Oh boy. Yeah, I'm gonna have to think about how to incorporate all of that stuff.
Totally
Cool.
unrelated. Why is it we can't have a timeout on a send or a receive?
You mean
Wow.
in the blockchain context in our node?
I guess in the real calculus sense, really.
Oh, I can't. Yeah, that's
Yeah, I was thinking of this system process also. Just to say raw timeout. If you want to execute something, but you want to wait after some period of time. If you want to start again, and so that would be like a useful system process to just say after this timeout, after this period of time, start again.
And
Yeah, I think that's not so hard once you assume you have a notion of time, but like that's the
Yeah.
whole thing about error correcting codes or time injection or something. Like if you're happy
Right.
just choosing
Yeah.
one of the methods, it's good enough. I don't think making the timeout is very hard beyond having a sense of time.
Yeah, but this time should not be part of the blockchain, right? This should be just rolling stuff.
Oh, I mean, I definitely agree. It's easier when you don't have to get distributed consensus. I don't know if I totally we shouldn't have time on the blockchain.
Yeah, I don't
I
know.
was thinking we could have timestamp. When you validate it, you just believe it.
Yeah, that's what Bitcoin and Ethereum do, and like in Substrate they call that an inherent, like something that comes into the blockchain from outside that isn't a transaction, it isn't signed, it isn't even really known to be true in any sense other than it's true by definition. And if it's like, if it's such a ridiculous timestamp, if it's like a year in advance or whatever you consider ridiculous, then you just don't add that block to your chain. You're like, all right, that guy's crazy. Let's just get the next block that seems reasonable and use that one.
Right, and I guess the idea being that whoever evaluated it initially is going to assign the value, and the validators don't care when it came up, because it was outside the system. The same goes with, I guess there's a whole, there could be utility in having data like that for a lot of stuff. I don't know what we call it, but that could be useful. The other thing I was wondering is how hard would it be to support a peak operation? Whoops. Who did we lose?
I think that Isaac already implemented Peak.
Yeah, I got Peak in there. It's pretty easy with the way that the COM events are handled in K framework, because basically all I have to do is so Peak is the same as a regular COM event, except the send is not consumed and the receive is. So I mean that's all I have to do is delete the receive from the tuple space and leave the send.
I see. So a peak will essentially block until something is sent.
Yeah, well, my understanding was you could check the contents on a channel without actually consuming the contents.
Right.
And without waiting, right?
And without waiting.
I mean, you don't have anything to wait for.
Go ahead.
Oh, I'm just saying that you don't have anything that you need to wait for a peak, right?
Mm-hmm.
Right. Yeah, I guess I was thinking of another operation also of checking to see if anything has been sent to the channel.
Yeah, I think that's what P does. So you're deploying formatting at some channel, a continuation, and if anything has been sent to that channel, you're continuing. Is just standard out, bang, something was sent.
Yeah.
I wish we could hear that.
Yeah, it sounded like he was just saying Peak basically does that. It checks and I think what he was saying was you can kind of you can just have it send you know, a message to standard out, like there is something on the channel or maybe that there isn't.
But if the peak isn't going to fire until something is sent to the channel,
Yeah.
then you don't know if there's no way to see if nothing's been sent to the channel.
Yeah.
My
understanding is that's not possible with since we don't have any synchrony constraints.
Yeah, that's exactly what I was going to say. Teeing that nothing is sent might require a synchronous calculus.
Yeah.
Well, we can do synchronous things. Actually, I was thinking in terms of garbage collection and some other things. But yeah, I guess it's difficult to do.
Yeah.
One other question. If you have on one channel, if you have one continuation that's waiting as a peak and one that is waiting for it to consume.
Yeah.
You will choose only one or the peak will be executed always.
I think it depends on which one executes first. If the peak executes first, then it will consume the peak, but the send will still be there, and that can com with the other receive. But if the receive consumes the send first, then there's nothing for the peak to do.
Makes sense.
It's strange.
It is strange. It's all a little bit strange.
Because you're just peaking. You're not changing anything. But sometimes you will see execution, sometimes not.
Yeah.
It's the same case though when you have two people, reading. So sometimes.
But if you write.
Won't.
Yeah, but if you now write a peak. Sorry.
If you consider, the use case that I think for peak is where you want to look at it and say, is this for me?
Mm-hmm.
And
but how do you do it now? You receive on this channel and you immediately write, right?
Yeah.
So in that case, this other receive will definitely receive a message, because if you receive it first, you will send it back, and this other receive will execute. right?
I guess, I mean, the only real use case is where you want to get the current value of a cell.
Mm-hmm.
Okay, and
Hmm.
you probably want the most recent one. So if it's in use right now, and that means it's going to change, and as soon as it gets the new value, your peak will fire.
Yeah, what was the original purpose for adding the peak feature?
So you didn't have to always rewrite the channel when you just wanted the value.
Okay, okay. And that's the use case for just wanting the value.
Right.
Yeah, okay. I guess that makes sense. Yeah.
So we outdid ourselves.
Yeah, I know.
Thank you again. I'm gonna.
Oh yeah.
I don't know if you want me to leave the room open.
Oh, I mean that's up to you. I'll probably continue working on this stuff today. But yeah, thanks for joining me for this long, guys.
Yeah, thanks for the presentation. It was really helpful.
Oh, cool, great.
Bye, guys.
Yep. See you later.